Python tutorial, probability distributions. Probability distributions consist of all possible values that a discrete or continuous random variable can have and their associated probability of being observed. Classical or a priori probability distribution is theoretical, while empirical or a posteriori probability distribution is experimental. This topic is part of Business Statistics with Python course. Feel free to take a look at course curriculum by clicking link at description box below. This tutorial has an educational and informational purpose and doesn't constitute any type of forecasting, business, trading, or investment advice. Please read full tutorial disclaimer at the end of the video. An example of probability distribution is the normal probability distribution, which consists of all possible values that a continuous random variable can have and their associated probability of being observed. Its probability distribution function is bell-shaped, symmetric from its mean, and mesocurtic. Standard normal probability distribution consists of normal probability distribution with mean zero and unit variance. Any normal probability distribution can be converted into standard normal probability distribution through continuous random variable standardization. As a formula, normal probability distribution density function is equal to 1 divided by the square root of 2 times pi multiplied by sigma squared. Sigma corresponds to the standard deviation, while sigma squared corresponds to the variance, which is then multiplied by the exponential of minus, and within the numerator we have x, which is the continuous random variable, minus mu, which is its arithmetic mean, that result to the power of 2, and then divided by 2 times sigma squared. Normal probability distribution has a mean equals to mu, and standard normal probability distribution has a mean equal to 0. Normal probability distribution has a variance equals to sigma squared, and standard normal probability distribution has a variance equals to 1. Normal and standard normal probability distribution has a skewness equals to 0. Normal and standard normal probability distribution have an excess kurtosis equals to 0. The reason for that is that normal and standard normal probability distribution have a kurtosis equals to 3. Continuous random variable standardization is calculated as follows. It is equal to x, which is the continuous random variable, minus mu, which is its arithmetic mean, and we divide that result by sigma, which is its standard deviation. Great. So let's go into Python PyCharm IDE so that we can study normal probability distribution with greater detail. Excellent. So here we are within Python PyCharm IDE. The first step within the tutorial is to do packages importing. So we'll import NumPy as MP, pandas as PD. From scikit-learn, we're going to import preprocessing as SL, then scipystats as ST, and matplotlib.pyplot as PLT. The next step is to create our data variable done through data reading. So we create this variable named spy equals to pd or pandas.read_csv. Then we have within it the path to the data file, stored within the data directory, and the data file named probability distributions data. So that's a plain text file with .csv or comma separated values. Index column as date, and we parse those dates as true. So let's go ahead and open that data file. As mentioned, this is a plain text file with .csv or comma separated values. The first column corresponds to dates, and the second one corresponds to SPY adjusted. SPY is the ETF investment vehicle which intends to replicate the Standard & Poor's 500 index. Adjusted because this includes adjusted close prices which were adjusted for dividends and splits. Data has a daily frequency, and we have data from the beginning of 2007 to the end of 2015, therefore 9 years of data. So going back into the code file, the next step is to do the calculation of standardized daily returns. For that, the first step is to calculate daily returns, and we do so with the creation of this variable named rspy, which is equal to the previously created spy.pct underscore change one position. So this will calculate the daily arithmetic rate of return. And we do dot drop NA, so we remove any rows with non-availables within them. And the next step is to do the standardization of these daily returns, which is done at the following row. And we do so with the creation of the variable which has an S at the beginning, so we know those are the standardized daily returns, srspy, equals to SL feature from scikit-learn dot scale of the previously created daily returns. This, what we'll do is subtract their arithmetic mean and to that result divide them by their standard deviation. The next step is to print those standardized daily returns descriptive statistics. Below their title, we're going to print their mean with that corresponding standardized daily returns variable srspy.mean, its standard deviation with .std, and then we're going to print skewness with scipystats st skew function for those standardized daily returns, and we're going to print excess kurtosis for that same corresponding scipystats feature, but with kurtosis function of the standardized daily returns. And once we've printed those standardized daily returns descriptive statistics, we can continue to study the standard normal probability distribution. For that, the first step is we are going to calculate the number of bins for our histogram. This histogram will correspond to the standardized daily returns histogram, and on top of that histogram we're going to plot a curve overlay which will include the standard normal probability distribution. Therefore, we need to calculate the number of bins for which the sum of those corresponding standardized daily returns histograms densities add up into 1. Therefore, we do so here with hbins variable, which is equal to an integer with int, and within parentheses, we need to round this calculation. Therefore, we do so with numpy rounded, and within it, we do the following calculation. First of all, we divide that by 1 by np, that's again numpy, dot histogram, so we'll be calculating a histogram of those standardized daily returns, density equals to true. In this specific case, we won't be defining the number of bins. So from that calculation, we are going to get the 0th position, which is all of those bins densities, and we are going to sum them. And to that result, we are going to multiply it, and as we can see here below, we have also within parentheses the length, and again, numpy histogram of those same standardized daily returns, density equals to true, again without defining the number of bins, and we get the results at position 1. The results at position 1 correspond to the bin edges. That's why we need to subtract 1 here. So with that calculation, we get the number of bins for the histogram, which we do next with plt.hist of those standardized daily returns, with bins equals to the previously calculated hbins, density equals to true, and the associated label, which is the corresponding variable name. And then we're going to add that curve overlay, and we do so with plt.plot, and within it, first of all, on the horizontal axis, we have the sorted values for the standardized daily returns. On the vertical, we have st, again, scipystats.norm for normal distribution, .pdf, the probability density function, and the values for it will be the sorted standardized daily returns. The label, as we can see here, is the normal probability distribution with mean 0, standard deviation 1, therefore the standard normal probability distribution. We add the corresponding title to this histogram, SPY standardized daily returns histogram, vertical or y-axis label density, horizontal or x-axis label bin edges, legend at the upper right, and we show the chart. Excellent. So let's go ahead and run this code file. As I've done it before recording this tutorial, the code file name is already stored here, so I just go ahead and click run. Perfect. So that opens the running console here. We'll briefly visualize those descriptive statistics being printed and together the associated chart. Perfect. So first, looking here at the console, we have the standardized daily returns descriptive statistics. So first of all, we see that those standardized daily returns have a mean of minus 6.27, and notice here with scientific notation to the exponential of minus 18, meaning that we will need to move this decimal point 18 places to the left. Therefore, they had a mean close to zero as expected because of their standardization. Then we can see that those standardized daily returns had a standard deviation of 1, which again was expected because of that corresponding standardization. And then we see that those standardized daily returns had a positive skewness, and also they had a positive excess kurtosis, which we can also see here within that result. So now looking at this chart, we have SPY standardized daily returns histogram. On the vertical axis, we have density, and in this specific case, also empirical probability. Horizontal one, we have those being edges, which are in number of standard deviations from the arithmetic mean. According to their legend, we can see that, colored in blue, are the bars for the histogram of those standardized daily returns. And on top, we have in orange that curve overlay, which is the standard normal probability distribution with mean zero standard deviation equals to 1. So, going back into the console, specifically focusing on skewness and excess kurtosis, we see that those standardized daily returns had a positive skewness, which we can corroborate here within the histogram because of having a longer right tail. And looking at the excess kurtosis, we see that those standardized daily returns had a positive excess kurtosis. Therefore, going again back into the histogram, we see that those standardized daily returns, the blue colored bars, the corresponding histogram, had a more peaked type of distribution with thicker tails compared to that standard normal probability distribution as the curve overlay. Excellent. So now that we've finished studying standardized daily returns histogram together with this standard normal probability distribution, let's go back into the slides. And as mentioned previously, this tutorial has an educational and informational purpose and doesn't constitute any type of forecasting, business, trading, or investment advice. Please pause the video now so you can read the full tutorial disclaimer. Okay, so with this, we finish this tutorial. Thank you for watching.